All right, so second day of class here today, Wednesday, August 31st. Just a reminder, next Monday, of course, is Labor Day, so we have that day off. But also want to remind you that we have that mini exam coming up now in 12 days instead of 14 days. One day, I think it's September 12th, if I remember correctly. The mini exam is again on chapters 5 and 6, which I'm not explicitly going over in class, though I will go over it as I go through chapter 7. So I will review chapters 5 and 6 as I go through chapter 7. Just 7 here. And actually, I'm going to tell you right now, I don't think I told you this on Monday. For the mini exam, which is going to be half an exam and take about half a period, the questions are going to be pretty similar to those review problems assigned at the end of chapter 5 and at the end of chapter 6. I put the key up for chapter 5 yesterday. I'm basically going to take some of those examples and maybe change the numbers a little bit for the mini exam. Question?
Yeah, so is there any way you can put the textbook online for a bit, because the bookstore is out of books for this course?
I'm not able to. The publisher doesn't do that unless you actually buy an access code, as far as I know. So they still don't. You looked this morning?
I did. I filled out one of those yellow slips, and
okay.
I'll get an email when they come in.
Okay, I'm sorry about that. I didn't know that was going to happen. I think the best I can say is try to find somebody to work with in the meantime, and then hopefully it'll come in, and if necessary, maybe even see if you can find a used copy from somebody. If you ask around, somebody might have it. There are a lot of used copies floating around.
Okay,
just gotta find it. Let's look at Moodle before we get into the content again here. So I did put the solution key for chapter 5. Zoom in on that. On Moodle, I will put the one for chapter 6. Probably tomorrow. So these are the ends of the chapters, these problems that I'm assigning that you don't have to turn in. You're just working on them as much as you can to help you prep for that mini exam. Where again, we'll make the mini exam questions similar to a random sample of these review problems, okay? Definitely not all of the review problems, that would take too long, okay? So I gotta pick a certain number of them, maybe, I don't know, maybe 4 of them or something, to put on the mini exam, and that will be what you're testing on. I did put the lecture 1 Mathematica notebook on Moodle as well. So once you've got Mathematica installed, you can download that and you can look at the notebook if you like. You can see what I did and you can re-enter the code if you like, just to see what it does. You will be using Mathematica to some extent on homework. And so you are going to want to learn the basics. I'll try to focus on basic things that you should know how to do. I will do some harder things too, like some of those things that I showed you last time. You want to be able to use some basic things that I'll show you. I'll highlight in class. I'll put today's up there later today, and again, you can download those. I guess as far as the version you load, I think I recommended either 10.4 or 11.0. 10.4 is what's going to be on Bethel's computers. Perhaps that's the best one to pick if you haven't done that yet. If you have trouble with the activation code, email Eric Gossett, G-O-S-S-E-T-T, at bethel.edu. G-O-S-S-E-T-T, at bethel.edu, and ask him to send you an activation code if you have trouble. Links to the lecture video will be up here, so I've got that statistics one and also the first lecture for us up here now. I will post today's lecture up later today. You probably won't typically need to watch it, but maybe once in a while if you have to be gone for some reason, you can watch it, or if you didn't quite understand something and want to rewatch it, you can do that. I am doing this for a couple purposes, just in case I want to teach this class online in the future. And just in case I want to maybe do some group work in class, I can say watch the lecture and then we're going to do group work in class. Those are the 2 main reasons that I'm videotaping the lectures and putting them online. By the way, if you don't want the back of your head on the video, And if you prefer, you can sit over on that other side or something. Most of you are over here. Most of the people in the class the camera can't see. They're over here and also behind the camera. That's fine. You have the 2 online quizzes to do. We have an in-class quiz today. About halfway through the lecture, we'll take a break, take the quiz. Maybe 5 or 6 minute quiz or so, hopefully. And you can also take a 1 or 2 minute break, just to stretch or maybe run to the bathroom and go real quick. And then we'll start the second half of class. There's going to be a lecture A and a lecture B. I should also probably point out that up here, besides the Mathematica installation instructions, this is a link to some video tutorials on using Mathematica that Wolfram made. Don't do the free-form linguistic input. Mathematica can try to interpret what you want to do. But we want to try to do correct syntax because that'll help us do better things. If we can be more careful at the start, we can do more fancy things later and not make mistakes. And this is a file that's got some suggestions and frequently used inputs, sort of like a cheat sheet to remind yourself of something. What's lecture A going to be about? Integration by substitution, both indefinite and definite integrals, and their relationship to the fundamental theorem of calculus, and actually also the chain rule, I could say. Maybe I should add that. And the chain rule. That's going to come this way too. And in lecture B, we're going to apply these ideas to some applications: probability, motion, area, and average value. All right, so let's do some examples. We'll try to start maybe as simple as we can here. Say you wanted to integrate 2x times x squared plus 4 to the 10th power. How's that come up on the video? Can you zoom in on it? Is that okay?
It's good.
Seems good? Okay. There's actually 2 strategies you could use. You could try to expand x squared plus 4 to the 10th power, right? Multiply it all out, and then multiply everything by 2x, and then integrate, or use what's called the substitution. And the substitution way is definitely better. Because if you had to expand this out, expanding something to a 10th power, this is called a binomial. You can use something called the binomial theorem, which maybe you recall involves using Pascal's triangle. And with a 10th power, you'd have to go way down in Pascal's triangle to look for the coefficients you need. Or you could use combinations, if you know about that, to help you expand this. It would be a big pain. I can actually have Mathematica do that real quick here, just to show you how nasty it would look. Let's go ahead and expand out this thing, this integrand, 2x times, in parentheses, x squared plus 4 to the 10th power. Actually, if I just enter this as is, I'm not sure if it's going to expand it or not. I might have to use a command. Let me just do a quick enter. It did not expand it. It just spit it back at me. All right, to expand it, there is a command, a built-in function called expand. Built-in functions in Mathematica, you should know, always start with capital letters. And their inputs always go inside square brackets. Expand is an example of a built-in function or command that will take this expression and expand it. There it is. Yes, you don't want to have to do that by hand. I think you could if you gave yourself enough time. You could expand this and integrate that. There's a better way. Substitution. Many books use the letter U for substitution, and they call it U substitution. Our book purposely avoids the letter U. They have a good reason for that, because the letter U also comes up in something called integration by parts, and they want to avoid confusion with integration by parts. They use the letter W. There's another good thing about using the letter W instead of U that will come up in a few seconds here. You want to let the new variable, u or w, it doesn't matter what you do on your homework. You could use v if you want, doesn't matter. You want to let it be, in this case, this expression inside the parentheses that if you did it the other way, you'd have to expand. How do I know that's the right thing to let w be? Well, partially because you often try to guess when something's in parentheses like this to a big power, or maybe it's inside a cosine function or sine function. Often that's a good guess. However, it's not always a good guess. You also want the other thing, the other factor of your integrand, to be either the derivative of what w is, or maybe a constant multiple of the derivative. If this is w, if w is x squared plus 4, then 2x is the derivative of that with respect to x, and that's good for the method of substitution. And here's where it gets fun to use the letter w, because if you use the letter w here, and you find dw dx, that's kind of fun, because that makes me think, hey Arthur, dw. I love Arthur. You know, my kids are now in their early 20s and late teens, and they love watching Arthur. I love watching Arthur too. dw dx instead of du dx. So another good reason to use w. dw dx, the derivative of w with respect to x is 2x. That's the extra factor that's there. It's common, and I think a good idea, to pretend now that this is a fraction. It's really not a fraction. Here's a funny confusion for many people. It's really not a fraction. It's the derivative. It's really a limit of difference quotient, so a limit of fraction. But it, in and of itself, just represents the idea of the derivative. It's not really a fraction. But oftentimes, it doesn't hurt to pretend it's a fraction. Gets you to the right answer. And that's an example of something we're going to do here now. We're going to pretend it's a fraction. We're going to pretend it's a fraction, and pretend we multiply both sides by dx. Write it this way. I think it is a good idea to do that. One of the founders of calculus, Leibniz, Newton and Leibniz were the founders of calculus. This is actually called Leibniz notation for derivative. By the way, you spell Leibniz. L-E-I-B-N-I-Z, and I think he was German. So E-I sounds like an I, and a Z sounds more like ts. You say Leibniz. That's Leibniz notation. And if I understand my history right, he actually did think it was a fraction. And there are certain modes of thinking you can have where you can think of it as a fraction. It's not really rigorous, though it can be made rigorous with really, really high-level math that we don't want to get into. Okay? He sort of took an intuitive approach, which was a little funny because he was a logician too. I think he knew he was on shaky ground, but he went ahead and did it anyway. Which we do now anyway. Pretend it's a fraction, multiply both sides by dx, and write it this way. And once I've done that, now I see that what I've got here is a w to the 10th power, and I also have a dw. The 2x dx is the same as dw, and it doesn't have to be right next to the dx, because I could move it over there. This integral becomes the integral of w to the 10th dw. And hey, that looks like a nice and easy integral, relatively speaking. Of the type you should be able to do on today's quiz. A power function, one of the memorized integrals. The n is 10 here. I have to add 1 to that to make it 11, and also divide by that same number. Don't forget your plus c. And on the quiz, you should make sure you include the plus c for full credit. That's today's quiz and some future quizzes too. Include the plus c for full credit. On the gateway, if you forget the plus c, it's no credit. Mostly because we want to allow ourselves to find particular antiderivatives to solve differential equations, really. You have to allow for an arbitrary constant to help you solve the differential equation. So it's an important thing. We're not done. You have to re-substitute back in terms of x now. W is x squared plus 4. I can leave it as something to the 11th divided by 11, or I could write it as 1/11 x squared plus 4 to the 11th plus c. I like the That board shakes so much, but that is an 11 there. You should always check your answers. Okay? Differentiate the function and see if you get what you started with. You can circle this, but let's also differentiate it. Oftentimes I write d dx, maybe next to an arrow like that, if I am emphasizing I want to differentiate something, in this case with respect to x. This is sometimes called the d dx or derivative operator. Differentiate what you see there is the idea with respect to x in this case. What do you get? Well, you have to bring down the 11. I get 11 over 11 times x squared plus 4 to the 11 minus 1 power, which is 10. Don't forget what? Chain rule, yeah. The inside function here is x squared plus 4. The chain rule says to take the derivative of the outside function, which is 1/11 x to the 11th. Bring the 11 down, get 11 over 11, which is, of course, 1. The inside function to the 11 minus 1 power, but don't forget to multiply times the derivative of that inside function there, the x squared plus 4. The derivative of that is 2x. The 11's cancel to 1, and you get 2x times x squared plus 4 to the 10th. You get the original integram right up there. It checks. In fact, every time you use integration by substitution, when you check it, you will end up using the chain rule. Because at a fundamental level, integration by substitution sort of is the reverse process of the chain rule. And we'll talk about that in a little bit here. Do another example. I'm going to make this example a bit trickier. Trickier looking at least. Integrate sine of square root of x divided by square root of x. This is really going to annoy me. Stay still. Maybe if I lock it, but then it swings too much. I'll try not locking it there. Okay. Most people look at that integral and think, oh, that looks kind of hard. And it is a bit tricky, but once you see the trick, it's not too bad. I said oftentimes you want w to be the thing inside the sine in this case, or the cosine, or raised to the, say, the 10th power. That's not always the case, that that's what you should do, but it oftentimes is, just by the way examples are constructed. But is its derivative, is the derivative of square root of x anywhere to be seen in this? What is the derivative of square root of x? Can you do that in your head? 1 half.
1 half square root. About 1 half times the reciprocal of the square root of x.
Yeah. Yep. 1 half times the reciprocal of the square root of x. If I let w equals square root of x, which is the same as x to the 1 half, dw will be 1 half x to the negative 1 half dx. I skipped a step there compared to the last example. I did not bother writing dw dx on the left. I just went right to solving for dw. If you don't like that, you can put the intermediate step. You can write dw dx is 1 half x to the negative 1 half, and then quote unquote multiply both sides by dx. I skipped that intermediate step, what I usually do. And yes, that is the same as what you said. What's your name?
Jesse.
Jesse?
Yeah.
That's the same as what Jesse said. 1 half times the reciprocal of the square root of x, or if you prefer, 1 over 2 square root of x. Yes. By the way, when you write this kind of thing, do include the dx on the right side, okay? It's sloppy not to. I mean, people can still get the right answer without doing it, but it's sloppy not to, and I think I'll tell the grader to be picky about that. So when you write it this way, do include the dx on the right. All right. Is that in there anywhere? Well, kind of. I see we're dividing by the square root of x there. I don't see a 2. Can that be adjusted for? It can be. One way to think about adjusting it is to take this equation, dw equaling this, and multiply both sides by 2. You could say 2 dw is 1 over square root of x dx. Another funny thing here. This is not really a literal multiplication. We're just pretending it's multiplication. Gets to the right answer. That's not usually good enough in math for justification. But again, we just kind of don't want to go too far into the reasons here. I will justify it a bit, but it will be an informal justification. In other words, I mean, this fraction here can be thought of as 1 over square root of x times the sine of square root of x. That 1 over square root of x now, combined with the dx, is the same as 2 dw. So this is going to become 2 sine w dw. I haven't integrated yet. I did the substitution, but I haven't integrated yet. Now integrate. Integral of sine is what?
Negative cosine.
Negative cosine, yeah. The 2 just gets carried along to the right. You get negative 2 cosine w plus c. Now substitute back in terms of x, negative 2 cosine of square root of x plus c. Check your answer. Differentiate with respect to x, d dx. The derivative of cosine is negative sine, so the derivative of negative cosine is sine. And the 2 gets carried along to the right again. 2 sine square root of x. Then don't forget about the chain rule to multiply times the derivative of the square root of x, which is 1/2 x to the negative 1/2. The 2's cancel, and you're left with sine of square root of x divided by square root of x. That is the original integrating that we integrated. That this is correct. And we use the chain rule. Let's do a definite integral. Time goes by fast. We're already getting close to quiz time here. Goes by fast for me, maybe not so much for you. Okay, do a definite integral. That's an indefinite integral. I do remember the plus c in the last example, right? Yeah. Okay. If I forget a plus c, and you say, hey, you forgot your plus c. We're going to make this a definite integral and review the fundamental theorem of calculus. Let's integrate this from 1 to 2. Which, I will also remind you, can be interpreted as a signed area. Actually, this graph for positive x is going to be above the x-axis, so it'll be an actual area under the graph between 1 and 2. I'm not going to bother graphing this. It's probably just going to go up really fast. Yeah, it's going to look like that. It's going to go up really fast is what the graph will look like. This could be a very big area, even though x is only going from 1 to 2. I'm going to do the substitution, and I'm going to do it in a way that maybe you are not used to. Maybe when if you took calculus before, well, you had to take Calc 1. In your Calc 1 class, maybe your teacher found the antiderivative first with an indefinite integral and came back and evaluated the definite integral. That is okay for the purposes of getting the right answer, but I want to emphasize something else. I want to emphasize that when you have a definite integral and you're using substitution, that you can stay in the new variable and never go back to x again? I can stay with the w and never go back to x and still get the right answer. But I do have to change my limits of integration. And I want you to do it this way. I'm going to tell the grader to look for this. I want you to do it this way because I want you to get used to it. It's not necessarily superior for this kind of problem, but in multivariable calculus, if some of you take that, which some of you probably will, it's definitely beneficial for the purposes of new coordinate systems to change the limits of integration. So it's good to get in practice with this. In this case, again, oftentimes, but not always, try to come up eventually with an example where the not always actually happens. You want to let w be the thing that's inside the sine or cosine, or in this case, the exponent of the e, and yet the thing that's there that's multiplied times it is a constant multiple of the derivative of that. I made it that way on purpose to make it as easy as possible. Let w equal x to the fourth. Then dw dx would be 4x cubed. So dw is 4x cubed dx. Which is almost what you see there, except there's no 4 there. So to solve for x cubed dx, divide both sides by 4. 1/4 dw is x cubed dx. It's probably the best way to do it to avoid mistakes. So you want to replace x cubed dx with 1/4 dw. And replace that with the w. Don't stop there, though, with that integral. Change the limits of integration. If you want a definite integral here, the answer is going to be a number, not an antiderivative, not a family of functions. It's a definite number. You've got to change the limits of integration by using the substitution formula. When x equals 1, the lower limit of integration, w equals 1 to the 4th, which is still 1, so that remains a 1. But when x equals 2, w is 2 to the 4th, which is 16. The 2 becomes a 16 now. Now do this integral as is and don't go back to x. If you try going back to x, you'll probably get the wrong answer. You'll probably do something wrong. You have to go back to the original limits of integration. Antiderivative of e to the w is e to the w plus c. Do you need the plus c here? For definite integrals, you don't, because if you included it, it wouldn't matter because you'd subtract it away anyway. So you don't need to put the plus c for definite integrals. There you have it. There's the answer. 1/4 times e to the 16th minus 1/4 times e to the 1st, which is e. Or you can factor the 1/4 out. You can factor a factor of e out as well if you like. Doesn't matter. You can write it either way. Let's get Mathematica to check this. And here's something you should be able to do on Mathematica, including for some problems at the end of chapter 5. Go to this palette menu, and you can go to any one of these three. I usually pick the first one, Basic Math Assistance. It's going to put a palette in the window here, which is this thing with a bunch of buttons. And open up this thing that says Basic Commands. No, don't do that. Typesetting. Notice there's a bunch of buttons here, one of which looks like an indefinite integral right there, and another which looks like a definite integral right there. Click down here so you see a horizontal line. That means Mathematica is ready for input. Do math. Click the definite integral button in this case. Look at their original problem there, put a 1 for the lower limit of integration, tab up, and put a 2 for the upper limit of integration, tab over, put your integrand, your function here, x cubed e times x cubed times e to the x to the 4th. By the way, if e to the x to the 4th, you understand the order of operations that you would raise x to the 4th power before you do that. In Mathematica, don't do a lowercase e by itself. The quickest way to get e in here is a capital E. That's the number e. I would recommend using parentheses like this to make sure it does it right. Oh, and I forgot my x cubed. Don't forget about that. X cubed. I think I'll use parentheses here just to be careful there too. A times is a star. That's the integral that we want. Hopefully it's going to write it as one of those answers that I wrote there. Do a shift return when your cursor's on that cell. And it wrote it in the second form. 1/4 e and e to the 15th minus 1, same thing. What is that approximately? Here's a little trick. A percent sign refers to the preceding output. So if I put a percent sign there, and if I do // capital N, that's a quick way to get a numerical approximation of the previous answer. The percent sign refers to the previous output. The capital N does a numerical approximation. The // just makes it work, essentially. Pretty big number, that's 2.2 million. That's how much area is under that graph. That graph's so high that the area under it between 1 and 2 is over 2.2 million. Wow. I did use the fundamental theorem of calculus here in the form you're used to. I call it the definite integral evaluation form. To find this definite integral, find the antiderivative, plug in the limits of integration, and subtract. That's the definite integral evaluation form of the FTC. There are other forms of the FTC that we will talk about, maybe even some after the quiz, but let's stop the video and take the quiz.